So he said I would know the topics. So the way you do this, you would train, he says it's easy for humans to generally do this. So in order to get this, to solve that particular problem, you would have to have labeled data. You'd have to say, okay, these are a whole bunch of text sequences related to this topic, and these are a bunch of text sequences related to this topic. And you feed these these sentences through. What you should get, you should have the internal representation at the end of this text string will be the CLA's best representation of what that thing is, and then you would just put it through a simple classifier. We've done this quite a lot. And then you basically say, okay, we're just going to classify those internal states of the CLA. That generally works pretty well. We've done that a lot. And I think that we have a classifier in the source code that's out there now.
Yeah, I think it KNN and SVN.
So that's a non-biological thing, but saying, okay, it's like reading the internal state of the brain and say, okay, let's just put that in the classifier, because that internal state actually represents everything that the CLA knows about the world and that particular string of text.
It'd be nice to know from him how in the brain it classifies things, do we?
Well, those kind of sparsely distributed representations are built up through the same process, but probably through the hierarchy. So this is a guess that you can shortchange that. It'd be like, we don't actually feed words into the brain, right? We feed sounds and we feed visual patterns and so on.
Yeah, but somehow we were able to look at something and say, oh, that's a chair.
Well,
so,
yes.
Getting to that kind of language.
So in this case, we're jumping right in saying we have a semantic representation. It's a relative semantic representation of these words. We don't actually have to assign the meaning to what those semantic bits are, although I guess in this technique you would pick. No, you just pick. You don't even do that. You say I want 2,000 concepts. So we don't need to know what those semantic representations, those bits mean. As long as it really helps you understand what we're talking about if you have a sense of what these sparsely distributed representations do. But again, you have these long bit strings where each bit means something, and then you're picking the top representations for that thing. So two representations, if you had two words, they would overlap in certain bits where they have similar semantic meaning. And I can take another word, and it would map a different set of semantic attributes. So the math of sparsely distributed representation says that you can take a word and almost any other word you show it, it'll tell you what's common between those two, and it'll do it in a very sort of brain-like way. So this solves sort of a major representation problem.
I guess where I used to, I'm a graduate student over at Portland State, and I used to work on a project that worked on object recognition and images, classifying, whether or not there's a tree in the image, stuff like that. I don't know if this would be useful for that, because it's more of a time-based thing.
It actually would be useful. If you're interested, I can talk about vision a bit. So right now, the state of the art in vision is a lot of people doing deep learning techniques, if you're familiar with that.
Kind of. I don't.
Well, the basic idea that everyone studies, most people study vision, by the way, studying image classification. They're not really studying vision. They're kind of trying to classify images.
Yeah, there's still images.
There's still images, and they're saying, that's not how we see. But even in that case, in the biological business, it's all about extracting a series of hierarchical representation where you figure out some sort of better feature space, and all these techniques that people use, and there's variations of deep learning. There's HMAX, there's convolution neural networks, and something like that. HMAX is hand-coded features, but they all work on the basic idea. What you're trying to do is build a sort of low-level features and high-level features and that and so on. And then a lot of people say, okay, the way the brain really solves this is that they do some form of what we call temporal pooling. They say, at any point in time you have an image, and then the image is shifted a little bit. Well, those two images really don't overlap at all spatially. If I took a hammer distance between them, they're completely different. So you can't say those two images are similar, but because they occur in time, you can say that they're the same. And so that's called temporal pooling. It's saying, okay, this plus this plus this plus this, these are all the same thing because there's a continuity in time. Oh. And HMAX does that temporal pooling hard-coded. They hard-coded it, which is not a very flexible way. Yeah. And then if you talk to the people in the deep learning community, for those of you, I don't know any machine learning people here, but so I've had a lot of discussions recently in the deep learning space. They don't really do this well. They don't really have time yet. So deep learning, which is the current state-of-the-art machine image classification, most of the people in that space will agree that they have to add this sort of temporal pooling. And so they have to add sort of sequence memory, because that's how you do it. You have to learn what typical patterns follow.
Something like a video.
Yes, you have to. So the way we learn to recognize images or something is we actually manipulate objects, and they're moving in our space, and a child will turn them around and play with them. And this is how we're learning this is how we're learning that these things are the same, right?
Right.
So anyway, actually, a lot of the CLA was developed with this vision in mind. Although I don't think it's a great place to start, because it's in the brain. There's a huge amount of cortex dedicated to low-level vision. It's monstrous, and it just shows you how much memory is involved. And we started doing some vision experiments with the CLA, and they're just taking forever to run.
Yeah.
So,
It is really computational.
yeah, so we think we know a fair amount of how it works and how the CLA should work in that space. But today, and we have some people on the mailing list who are interested in this, but it's a little scary for me.
Can you do it with synthetic targets that are simplified so that they can be more readily distinguished?
Yeah,
Yeah.
this is what we were doing.
That's what we were doing for many years. But even so, the space explodes quite a bit. And what we found is we had to do all of these computational tricks to just get things to just even converge in a reasonable amount of time.
Yeah. Let me explain. It wasn't algorithmically taking a long time. It was just that if you're modeling a large piece of cortical region, it just took a long time for our software to do it. It wasn't like it was a convergence problem. That wasn't the issue. It was just, our experiments would take a long time to run. So what we would do is we would cheat a little bit. We'd say, okay, we're assuming that the statistics in this part of the visual field are equal everywhere. And so we don't need to learn them everywhere.
Or was that copying code?
The cloning, yeah.
We were cloning. We were basically cloning part of the visual space. We learn a little piece of it and go, okay, blah, 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 blah. But to get that to work right and to get it all seen, there's no divisions here. It's all one continuous thing. So to get that to work right, we did a lot of tricks and a lot of stuff. And we're just pushing the limit of what can be done in software today.
So do you see, let's say we move this to hardware and get, 1,000, 1,000,000 times speed up, is that doable then?
Yeah, sure, obviously. I mean, we'll
So there's nothing wrong with the technique?
as far as we know, I
The
mean,
data is
as
just-
long as,
Yeah.
yeah, so this,
We proved it out even for up to, I think, 3 levels of hierarchy that with the CLA, you can actually get a lot of the properties that you want. It just took an incredibly long time to train and tune the parameters.
we were just spending all of our time just trying to do shortcuts.
So the trick now is to put some energy into encoding so you digest a lot of this.
Well,
Maybe not with
we just
vision,
moved to
but
other
other things.
problem
Yeah,
spaces.
Exactly,
Yeah.
and other problem spaces, the same thing. Right?
Yeah, they're just much smaller.
So
problems.
just to give you an example, I've said this many times, but in the actual physics, your cortex, there is a huge amount of stuff dedicated to low-level vision. It's far, far greater than the total space dedicated to language. The language areas are quite small. Actually, language is much, much easier than low-level vision from a cortical tissue memory allocation space. Because what's going on in the low-level visual space is you're basically having to learn all these invariances over a large sensory array. But once you actually get into the language regions, there's no topology anymore. You're just learning sequences. Where in the beginning of the visual space, it's just got this monstrous million-bit field coming in, and it has to be.
It's like 40 or 50% of the neocortex is